do it the way you want to do it. Okay, so today we're going to pick up and kind of continue talking about sets. So last time we talked about the idea of a set. We talked about some of these special sets and relationships between them and some pretty high level, like theoretical algebraic stuff that we understood to varying degrees, but maybe were kind of wowed by and surprised by the results there, which was kind of what I was going for. Today, we're going to talk about another kind of a set called a relation. So we'll start just with a definition. So a relation is a set of ordered pairs. Again, if you don't immediately recognize that piece of vocab, when we say ordered pairs, we're talking about like a coordinate, like an x comma y, just like from geometry last year, where the x values come from a specific set that we call D, and the y values are coming from a specific set called R. In general, we call that set D the domain. And we call the set R the range. So just like a little example about what we mean here. So a relation is just a set, so we'll name it with a capital letter. Then we'll use the little squigglies next to it. And if it's a finite set, I just might write down on a, just might list them explicitly, the ordered pairs that are in our relation. So this relation has 4 ordered pairs in it. Everybody okay with that idea? So if I wanted to talk about the domain for this relation, the domain is also a set, and it's the set of the x coordinates, right? Whereas the range is the set of the y coordinates. Everybody okay with that idea? So I might ask, is the number 1 an element or a member of set A? What do we think? The answer here is no. Remember, the items in set A are ordered pairs. So 1 is not even in the proper format to be a member of a relation. You have to be an ordered pair in order to be a member of the relation. But 1 is a member of the domain. Everybody okay with that distinction about the difference between the two? And that's subtle, right? Initially, most of us said, yeah, 1 is a member of A, until we kind of back out and remember the definitions of what we mean by a relation. It's like, well, they have to be ordered pairs. So if we ask, is 1 comma 2 a member of A? That answer is yes. Everybody okay there? Again, just wanted to take some time and make sure we really understand the definitions with some concrete examples. Nothing that we've done here is super difficult, like it didn't require any calculation. It's just about understanding the definition and being able to like apply that. So there's nothing really to write down. There's no work to really be shown. We're just kind of using some definitions to answer some questions, right? So the only place where we could get into a little bit of a hiccup here when we talk about the domains and ranges is a situation that kind of looks like this. So let's say this is our relation. And let's say I go to write down my domain. What would I write down for my domain? I'm sorry, what? 1, 3, 4. Very good. Notice what didn't, let me give you some specific credit. Sydney, right? Okay. What didn't Sydney do here? You didn't list 1 twice. Why not? Because they're the same value. Remember the definition of the set? Says it's a list with no repeated items. So the place where you can make a mistake here is if you're listing a domain and range, and even though the coordinate is used more than once, you cannot list it more than once. Only one time do we list things. Is everybody okay with that? So, good job, Sydney, by only listing 1 once. That's exactly what you wanted to do. And I'll just write there in red that it's wrong to list the 1 more than once. Everybody feel good here? So these are both examples of finite relations because there's a finite number of ordered pairs in our relation, right? What would it look like if I were to write an infinite relation? Well, we're going to have to use that other set notation that we talked about yesterday. So the things in my relation look like ordered pairs. They're going to be an x comma y, right? And then I'll have to list some rule as to how I determine the x, y's that are in there. So maybe I want to write a rule like something easy, like y equals x. What are the things inside of, let's not use a. We already used a. In this example, let's change that to a C. That'll be less confusing later on. What are the ordered pairs in C going to look like? What's an example of something that might be in C? Yes. 2 comma 2. Right? Why is 2 comma 2 in C? Because the x and y are the same. Everybody's okay with that? So I can just use the rule to generate something that would be in that set. More often than not, when we talk about an infinite relation, and we're using like a set notation to describe it, your rule, I guess I should say, is going to be an equation like a y equals whatever equation. Something that looks pretty familiar. Okay with that? Now, it doesn't have to be that way, but for a class like this, it would be. Like we're not doing like theoretical, like abstract algebra here. Which if you go on and you do like a math major in college, you'll probably have to take an abstract algebra class, and you probably won't really see a number like the entire term, which is fun. It's a good course. Anyways, everybody okay there? So again, I just wanted to reiterate what a infinite versus finite one will look like from a notation standpoint. Okay. Next up, let's talk about the 4 different ways that we can represent a relation. So the first one is as a set of ordered pairs. Which we've just been talking about. So we probably don't need to do another example of that right this second, right? Everybody agree with that? Another way we can do this is with something called a mapping diagram. And really, we only use the mapping diagram in finite situations. That you can't really use it for an infinite one, since it's a visual. So with a mapping diagram, we have one oval for the domain, and another oval for the range. And we're going to write down the members of the domain or range. And then we're just going to use an arrow to describe the pairings that are going on. So the idea here is that each one of these arrows would represent an ordered pair. So this first arrow would represent the ordered pair 1, 2. This next arrow would represent the ordered pair 1, 0. This arrow would represent the ordered pair 2, 2. And this one would represent the ordered pair 3, 0. Is everybody okay with that idea? So this is just me translating our mapping diagram into like a set of ordered pairs. So you can see that it's really just the same information. It's just a visual representation rather than like a symbolic representation. And you can probably see really easily why this is really only good for finite relations, because you can't list an infinite size domain or range and draw an infinite number of arrows. Like, can't be done. So really, we only do this for finite situations. Okay. The next one up is a graph. So if you have a finite relation, your graph is just going to look like points, right? Now, just because you have points doesn't guarantee that it has to be finite, but you can't be so if you have more than just points, you can't be finite, but just points alone doesn't guarantee finite. And we'll explain here in a second why. If you have any kind of a connected curve, this would be an infinite relation. If you have any kind of connected curve, you can't be finite. But there can be a situation in which you have points only and still be infinite. So let's look at a situation like that really quick. Oops. Points only, but infinite. So just as a little example here. I'm going back to A since we're in a new example. I feel safe to do that. So I'll use our infinite notation. So what if we have the set of xy's where x and y are equal, but x and y are both integers? Notice this is slightly different than the example that I gave before because I didn't have any requirement on where x and y were coming from. In that situation, you can just kind of assume that x and y are coming from the real numbers in a class like this. Here, though, they're coming explicitly from the integers. So what does this mean? It means something like 0, 0 is in A, and 1, 1 is in A, but there's nothing in between those 2 points that's also in A. Everybody okay with that idea? So if we were to graph this, or try to graph this, we have an infinite number of points. Let's do a different color there. We have just points, but there's an infinite number of them, right? Because there's no connection in between. Does everybody kind of see that? However, if I have anything that's connected, that guarantees it's infinite. There's an axiom from your geometry class that tells us why. Do you remember? How many points are on a line? Infinitely many, right? So if you have any connected segment, that's infinitely many points right there. So if you have any part of your graph is connected, it's automatically going to be an infinite relation because that part alone, any of the connected part, has infinitely many points in it, right? And that's just a natural extension of that axiom from geometry, which again, if you didn't remember, that's okay. Like I had to ask a different question before you jog your memory because you probably didn't remember that as an axiom because it's one of those that like we present at the beginning, but you never use it to prove anything because it's so kind of basic idea that you end up forgetting about it. But that's what's going on there. Is everybody okay with that idea? Okay. Okay, so our last representation is with an equation. And really, when we do these equations, in a course like this, we're just talking about infinite things. So the assumption in a class like this is that if I just give you an equation, the implied domain would be all real numbers. So that you're just, like it's already going to be infinite, Anyways, that would be the assumption, right? And again, like you can generate infinitely many ordered pairs with an equation like this, right? Okay, good. So let's talk about a special kind of relation. We call this special kind of relation a function. So we say that a function is a relation where every item in the domain pairs with exactly one item in the range. So just as a little comment here, we've talked about 3 types of structures here in the last 2 days. We've talked about sets, relations, and functions. Set is the biggest one. every relation is a set. And then functions is the smallest one. Every function is a relation. So we have the same kind of subset property going on here, where the set of all sets, the set of all functions is a subset of the set of all relations, which is a subset of the set of all sets, right? So this is just kind of a comment, and we're not actually adding any content there. We're just kind of reminding you about these three things and kind of how they relate together. And remember that symbol here that we're using, that's like the sideways union symbol with the line underneath it. That's our just symbol for subset. Again, if we write down a symbol that you don't remember exactly what it was because we've used it just once, feel free to ask. It's okay. If you're thinking it, I'm sure that many other people are thinking it, so it's okay to jog our memory. It's important for understanding that if you have questions along the way, you're not sure about something along the way, that we stop and ask. Or if you need me to move things up or down because you can't see it, please let me know. Happy to do that. Okay? All right, so what's up next? We're going to do a bunch of examples here. So we're going to do a bunch of examples. The instruction for these examples is we're going to determine if the relation is a function or not. And then we're going to write down the domain and range. So I'm going to use each of these four different representations. Some of the things that we'll write down will be functions, some will not be. We'll talk about why it is or isn't. What are the strategies we can use to kind of tell when it's this type of representation. And we'll talk about the domains and ranges and kind of how to deal with that. Okay, so we're going to do kind of a lot of things on these examples. Is everybody ready? Okay. So I'm going to label each different example with the letter A because we're going to do, I don't know, probably 20 different examples here because there's 4 different representations and we're asking you to do kind of a lot of things and we need to do a little bit of variety to make sure we got it. But I don't know how many total examples we're really going to do. I'm just going to kind of write them down until I feel like we've done enough of one type and just kind of keep on going. Okay. So the first one we'll look at is just a finite set of ordered pairs. So to be a function, we need to check 3 things. First thing we need to do is check to make sure it's a relation. Is everything an ordered pair? Yep. Okay, so we have that part. The second thing we have to do is check to make sure that everything in the domain is paired with something. Well, we have ordered pairs listed, so clearly that's the case. The last thing we need to check is to make sure that each of the x's, the domains, are paired with exactly one range. Is that going on? You say no. Why do you say no? 4 got paired to 1.
Oh.
Right?
Yeah.
3 gets paired only to 3, 2 got paired only to 2, and 1 got paired only to 2. This is a function. Each x is only paired with one y number. Did it matter that some of the y's were paired to more than one x? No, not if we're talking about functions. There's another property of functions that we'll talk about later where how many, like the number of y's that an x has, or the number of times a y gets paired with an x matters, but not here. not if we're just talking about something's a function or not. So basically, when it comes to a set of ordered pairs like this, all I'm looking for is a repeated x coordinate. I don't care at all about the y's. Everybody's good with that? Okay, so if we want the domain, what would I write down for the domain? Go ahead, Maddie. 2, 3, and 1 would be the range. That's good, because that's the y coordinates. 1, 2, 3, and 4 would be the domain. Very good. Everybody's okay with that? Does it matter the order in which I write down those numbers? No. Sets, the order of a set does not matter. You can write them in any order you want. Typically, I write them in like numeric order, but if the set is really long, the order in which they appear might be easiest to write down. But the order does not matter. You just need to have them in there. Everybody feel good on this one? Okay. Is this a function? No. Why not? Yeah. So the x value of 1 appears more than once, so we know it's not a function. What would the domain be? Yeah, it would be 1. Now, when we write that, you still have to make sure you put the set brackets around it. You can't just write 1. You got to make sure that you put those squiggly brackets around your number 1. I would not count it as completely correct without them, just as an FYI. It's an easy mistake to make, but it's okay. And the range we would say is 1, 2, 3, 4. Everybody feel okay here? The finite ones are typically the very easy ones to deal with the domain and range for. Okay? I'll come back and do that. No, I should do it now. I'll forget. Let's do an infinite one. And just to be clear, I'll put this in there too. So this is an infinite set. You can tell just by looking at the notation already, right? So let's think about how to tell if this is a function or not. Well, the thing that I'm going to use is the rule. I'm going to look at the rule. And the first thing I would want to make sure is that the dependent variable is isolated. So in this case, I'd want to make sure the y is by itself, which it is. So I'm good to go. And here I'm just going to pick some values for x and make sure that I don't get more than one value of y when I do that. So just do a couple of little test cases. So if I pick x to be 0, what does that give me for y? One number, right? So we tried 0. Let's try a positive, like 1. What does that give me for y? Still 1, right? Let's try a negative. What does that give me for y? 1. At this point, I'm pretty convinced of what's going on here. Is there any way to get an x that has more than one answer? No, right? We've done positive, negative, 0, and all of them are giving us one answer. And at this point, it should be pretty clear to us that no matter what we pick for x, we're just going to get a single answer for it, right? So what can I say about this? Is this a function? Yes. Right? Because the x's are used just one time. In addition, though, there was something else I should have checked. It is still a function, but we neglected to check this. We'd want to check and make sure that every real number can be used, since x, the domain we're told, is the reals. So again, you can plug any value of x in that and it's still going to give you a y, right? So we're good there also, but I should have made mention of that. Okay? Now let's do the domain. We've already kind of answered this, right? What's the domain? All real numbers, right? We just established that we can take any value from R, plug it into that rule, and get a y. So all of those x's work. So as an interval notation, we could write it this way. Or if you wrote it as an inequality, and you could write it this way. Or I guess as a strict set, you could say the set of x's such that negative infinity is less than x, which is less than positive infinity. Any of those representations I would count as completely correct, unless the directions specifically ask for, write your domains and ranges using blah, blah, blah form. Is everybody okay with that idea? Let's do the range now, which is maybe a tad trickier. So if I look at the rule, what kind of number is the range always going to be? It's going to be a real number for sure. Well, I would say a little bit bigger than positive. It should be non-negative, right? Because what thing other than positive can you also get? 0. Because if I look at this, notice that y is something squared, right? The result of something squared must be non-negative, right? You can't square a number and get a negative back. Or I should say you can't square a real number and get a negative as a result, right? But you can square 0 to get 0. And if you square a positive, you get a positive. If you square a negative, you get a positive. So what our range is, should be bracket on the 0. Is everybody okay with that idea? Because 0 is a possible y value, right? If x is 0, we do get y is 0. That did it? Okay. So remember, the bracket means is included versus a parenthesis means it's not included. So if it was, like if the range was only positives, then that would have been a parenthesis. But because it's non-negative, we need to use a bracket. Right? And the difference is just whether 0 belongs or not. So these infinite ones are a little bit harder to do, right? Everything about it makes it a little bit harder. Remind me, and we'll do another example of this at the end, but I'm going to move on and cover some more of these other situations before we run out of time. Not that we're getting close to running out of time. We still have a lot of time left, but I'm always just want to be careful to make sure I do some of everything before I go back and do a lot of something. I think we're on letter D, right? So here's a mapping diagram. Is this a function?
No.
Why not?
It's another pair.
Excellent. So we have something in the domain that's not used. So that's not a function. And what's the domain going to be here? It should be, it's as obvious as you think it is. 1, 2, 3. Like everything that's in the circle for the domain is your domain. What's the range? 0, 1, 2? Just 0, 2, right? Those are the only two things in the range. Everybody's okay with that? Okay. Let's do another like that. Oh, E is what we're on, I think. What's going on? 3/4? All right. How about this? Is this a function? No, why not? Good, which is 1. Excellent. And the domain for this would be 1, 2, 3. Notice that just because 1 was used more than once, the domain still has 1, 1 in it. There's a lot of saying the word 1 there. The range. 0, 2. So again, these mapping diagrams, especially really anything that's discrete, the domain and range are easy to do because it's just a list, right? You just list the points that are used or the x's or y's that are used, and it's those ones are usually quite easy, right? Jane? Yes. Sure. We have the x coordinate 1 that pairs with 0, and it also pairs with 2. So that x has 2 separate y's, which violates our definition. You're welcome. So to sum up here for these mapping diagrams, the two things we want to look at, we're looking at the x's only. We want to make sure that every x has an arrow that originates from it. And we want to make sure that every x has only one arrow that originates from it. Everybody's okay with that? Okay. So again, like once we've kind of figured things out, do a little sum up at the end. Hopefully this is helping, right? Am I going too fast? Sometimes I get excited. We're okay? If I get going too fast, you can please tell me that, hey, you're going too fast, slow down. I just get excited about the math sometimes, guys. All right. So here's a graph. This is a finite graph, though, because there's just 5 points involved. In a graph situation, you can assume that everything in the domain is used. Okay? So you don't have to worry about checking that part. All we really need to worry about checking in a graph situation is for repeated x values. What would 2 points with the same x value look like graphically? They'd be on the same vertical line, right? So if I had like 1, 2 and 1, 3, like 1, 2 would be there and like 1, 3 would be right there. Everybody's okay with that idea? So that's what we're looking for. And what we call this is really a vertical line test. I abbreviate that as VLT. And what the vertical line test says is if you can draw any vertical line that intersects the graph more than once, that graph is not a function. Now, I've used this abbreviation VLT. You guys are more than free to use the same abbreviation. Unless I tell you that I don't want you to use that abbreviation, you're welcome to use it if we've used it in class during the lectures. So if we look at the graph for f, is this a function? No, why not? Sydney, you were shaking your head. Yeah. Yeah, exactly. So if I look at these 2 points on the left, they appear to be on the same vertical line. Now it's hard to maybe have noticed that because my penmanship is less than spectacular. But on a test or a quiz or whatever, I would have used a computer to generate these and added some grid lines for you on the graph so it'd be easy to tell. Okay? Do we have to talk about how to do the domain and range for this? You just read the points off of the graph and write them down for the x's and y's. Since I didn't really assign them any x or y values, I don't want to go back and do that now because it's just kind of a hassle, but does anybody not understand what I'm saying here? Okay. So this is an attempt to be a circle. It's an okay circle, I guess, for freehand. Is this represent a function? No, right? Why not? Yeah, lots of vertical lines you could draw that would intersect this graph more than once. Does it matter that there are vertical lines I can draw that don't intersect the graph? No. Does it matter that there are vertical lines I can draw that intersect the graph one time? No. All that matters is that there is at least one vertical line that intersects the graph more than once. That's it. Doesn't matter if there's vertical lines that don't intersect it or intersect it once. All we need is one vertical line that gets the graph twice for it to be not a function. Everybody's okay with that idea? What's the domain going to be here? It's going to be infinite, right? Because we have a line involved, a segment involved, or an arc. It's connected. Everybody's agree with that? So we're going to have to use like interval notation or an inequality or something. I can't just list them out. So what I like to do is I think about, okay, what's the smallest x coordinate on my graph? -1. So that'll be the lower bound for my domain. And the biggest x coordinate on my graph is 1. Now, is there a point that uses -1 as its x coordinate? Yes. So that gets a bracket. Is there a point that uses +1? Yes. So that'll get a bracket. And I should have noted also that the graph is connected in between -1 and +1, right? That if there was a break in there, that's a different story. We'll look at an example here later where maybe we have a break. Yes? So the bracket means that that value is included. And because we have a point, that has that x-coordinate, that x-coordinate is included. Okay? We'll do an example where we wouldn't use a bracket here in a moment. Is that verbiage understandable, included versus not included? Okay. Let's do the range then. So the range is about which coordinate? The y. So we'll do it the same way. The smallest y coordinate used is -1. And the biggest? +1. And we're connected all the way in between, right? By connected, I mean like I could walk along the graph from the point where we have -1 as the y-coordinate to the point where we have +1 as the y-coordinate. When I say connected, you can imagine like a little person walking along the graph. Okay. Is -1 a y-coordinate in an actual point on that graph? Yes. So it gets the bracket. Is +1 an actual y-coordinate in an actual point on this graph? Yes. So it gets a bracket. B, C, D, E, F, G, H, I think is my next letter. 12:35, so we still have 10 minutes. Okay. We're doing good, folks. Let's do... So this here, what I've drawn, is a point that's not filled in. That's not like a circle on my graph. That's supposed to just be a point that's not filled in. I drew it kind of big because, well, it's hard to see on the projector what's going on. And I wanted to make sure we note that. But that's just like a point that's not filled in. Yeah, so it's like how I drew the point up here. That didn't work. Okay. Like how I drew that point there, but it was filled in. You know what I mean? This is a point that's not filled in. So what does that notation mean if I have a point that's not filled in? It's not included in the graph. So that's telling me that like this end of my graph goes right up to 0, 0. You know, it'll be at like -0.0000001, positive 0.00001, but it can't actually get to 0, 0. Does that, everybody's clear on what that's saying? Okay. Is this a function? We'll start with the easy question. Yes, right? Definitely passes a vertical line test, right? That shouldn't require a lot of explanation there. You guys agree? Now let's do the tricky parts, the domain and range here. So the domain, what's the smallest x value involved here? We have an arrow going to the left, so that means the smallest x value involved would be -infinity. Everybody okay with that? Now, instead of asking the biggest x value involved, I'm going to stop here because I notice there's a break in my graph. Where's the break in my graph? Well, it's at this open or empty point where the two halves of it aren't connected. Right? Does everybody see that? So it's really, I'm going from -infinity to the x-coordinate at that break. So I'm starting at the smallest point and going to the break in my graph. And the x-coordinate there is 0. Everybody okay there? Okay. I know that the -infinities always get a parenthesis. And because the point where the x-coordinate is 0 is not included in my graph, that also gets a parenthesis. Everybody's okay there? But now I have this whole other section of my graph here that I have to deal with. So I'm going to have a whole other interval, and I connect those with a union symbol. And here I'm going to start at the break in my graph, whose x-coordinate is 0, and go all the way to the biggest x value involved in my graph, which, because I have an arrow pointing to the right, is positive infinity. Is everybody okay with that? Let's do the range now. Does the break in my graph really affect the range? Not really, right? Because there's still just the smallest point and a biggest point, and the break doesn't break up going from the smallest to the biggest. You know what I mean? The smallest y-coordinate is 0, right? This is the smallest point, or the lowest point. Do you guys agree with that? And the tallest point, or the biggest y-coordinate, is positive infinity, because I have arrows that point up. Now, should I get a parenthesis or a bracket at 0? Parenthesis, because there is no point at 0, 0. And the infinities always get a parenthesis, right? Now let's say, just for the sake of argument, that we had the same graph, but I also had this additional point sitting here. What would that change? Would the domain change? Well, it wouldn't be a function. We can start there, not a function. Did that change the domain? Did I add in an x that I didn't have before? No, I didn't. I had that x already right there, right? So it's not going to change my domain at all by adding in that other point. Do you guys see that now that we look at it that way? Does it change my range? Yes. Now I have a y-coordinate that I didn't have before. What new y-coordinate does that extra point add in? It's 0, right? That's something, comma 0, right? So now I have the y-coordinate 0. So instead of having a parenthesis there, I would use a bracket. This was a very tricky example, okay? That's basically as hard as it gets. We're going to continue talking about this on next time, because we still have to talk about equation situations, which are not trivially easy. But I do want to say that we have done a lot of stuff, and you could start on the first homework